Hey everybody, and welcome back to Patel Academy. Today I wanted to do a similar thing to my last video and do a timed walkthrough of the free response questions for the AP Calculus exam, except today I wanted to do it for the AP Calculus BC exam in 2019. Now, because this is a timed walkthrough, once again I will be following the timing information, which is the same as the AP Calculus AB timing. So part A consists of 2 questions in which graphing calculators are allowed, and a total of 30 minutes is allotted for it. Well, part B consists of the remaining 4 questions where calculators are not allowed, and a total of 1 hour is permitted. So you will also see a little bit of overlap within the BC and the AB questions. Usually out of the 6, about 2 or 3 are repeated, and then 2 to 3, about 3 to 4 I'd say are unique towards the BC concepts or towards the AB concepts, but you will see some overlap between the 2 videos. Now the work will be a little bit different, but the concepts will remain the same, of course. So let's get right into it. So question number 1, this is one that overlaps with the AB, so please make sure to go check that video out to see how I did it, if there were any differences. And some of the other AB specific questions do have some unique problem solving skills over there that involve things that may not be tested in previous years on BC but could be tested now or in coming years, those kind of skills, so be sure to check that video out. Question number 1 gives us an entering function of fish into a lake of 20 plus 15 times sine of pi over 6 times t, and a leaving function or a loss function of 4 plus 2 to the power of 0.1 t squared. Now, first of all, before I even move on, like I said, you always want to input these functions into your calculator so that it's easy to call upon them and conduct operations on them. It also says here that both E at t and L at t are measured in fish per hour, and I see that that's a rate of change. Now why is that important? Well, because the rate of change models the first derivative, and so it's not the original function. So in this case, our original function would be the actual number of fish. In this case, E at t and L at t directly are the change in the number of fish, so we have to keep that in mind. And then finally it gives us that t is measured in hours since midnight. So we'll usually be working from midnight to a certain time, so t equals 0 to t equals some value. So let's get started with part A. How many fish entered the lake over the 5-hour period from midnight, so t equals 0, to 5 a.m., t equals 5? Give your answer to the nearest whole number. Now it's important to read the question carefully because these last statements, like give your answer to the nearest whole number or include units of measure, things like that will usually be worth a point, and so it's important that instead of that you answer the question the way that they want, not necessarily just plug it into your calculator and that's it. Remember to interpret it also if necessary. So for this first one, it's asking for the total number of fish that have entered the lake. So the change in the number of fish from time t equals 0 to time t equals 5. And so what do we know about rates of change? Well, if you integrate a rate of change or a derivative, you get the change in the original function. And so for this first one, all I'm going to do is I'm going to take the integral from 0 to 5 of our entry function e at t with respect to time. Now don't bother working out the antiderivative for this. It's much easier to just put it into your calculator, this expression. You should get the value 153.458. Alright, and then while this is what I was saying earlier, remember to interpret it in regards to what the question asks. So it asks us to give it to the nearest whole number. So we say that it's approximately 153 fish. It's our final answer, and even though it didn't specifically ask in this question, it never hurts to put down your units. It's a good practice to have, not only for the AP exam, but even for exams that you'll be taking outside of advanced placement. So it's just a good practice to always put down your units, and if possible, also have a full sentence answer at the end. Alright, so moving on to part B. What is the average number of fish that leave the lake per hour over the 5-hour period from midnight to 5 a.m.? So the same time interval we have, but this time we're asked for the average number of fish. Now keep in mind that the average value of a function is equal to 1 over b minus a times the integral from a to b of our function. And so in this case, we're trying to find the average value of our loss function, so the average value of the fish that leave the lake per hour. And so we do average fish, I'm going to say loss 1 over 5 minus 0 times the integral from 0 to 5 of, in this case we're using L at t, dt. And so 1/5 times this integral of L at t, you'll get the answer 6.059 fish. Now I will say, I did mention this in the last part, but I will say, when you're practicing, it's really helpful. I did iterate this in my last video, but it's really helpful to say the concepts or think of the concepts while you're practicing, so that not only do you get the time, you get to know how well you're doing in terms of time while you're trying to recall these concepts, but it also gives you a chance to review and make sure that you're getting everything accurate multiple times. So for example, in this case, I restated the average value function. That's an important practice that I think you should be using in your sample free response question when you're working through them, because if you can meet that 30-minute mark while you're doing this, while you're restating your concepts, on the actual AP exam, you'll be able to hit this first section in about 25 minutes, you'll be able to finish, and then you have that 5 minutes left to check. And that's usually what you should aim for, is about 5 to 10 minutes to check over all your work and make sure that you don't miss any arithmetic errors, because that's probably the thing that messes people up the most compared to the conceptual errors. Alright, so our average fish loss is 6.059 fish. And keep in mind, we don't have to do any rounding over here, so this is our final answer. And as you can see throughout this timed walkthrough, I like to double underline or maybe box my answers, just makes it clear as to what my final answer is if I don't give a full sentence statement. Moving on to part C. At what time between 0 to 8 inclusive is the greatest number of fish in the lake? Justify your answer. Alright, so I see greatest number of fish. What does this tell me? Well, this tells me that I'm working towards an absolute maximum, sorry. Oh my. Alright, and so what does that tell me? I need to use the candidates test. Or the first derivative test. And I also, keep in mind, I need to test critical points and endpoints. Alright, now to work through this problem a little bit more, we're asked to find the greatest number of fish in the lake, not the greatest rate of change of fish in the lake. And so why is that important? Well, it's important because we can't necessarily just use E at t and L at t as it is. And so one of the good practices to have in terms of problem solving skills is to create your own function in order to be able to work with whatever units or whatever values you need to. And so in this case, I'm going to define my total fish as a function f at t. And then I'm going to let this equal to, well, our rate of change of fish, our total rate of change of fish, is our enter minus our exit. Except if we want to find the number of fish actually, we should do this from 0 to some time t1, and then this integral is respect to time. So our f at t function is the integral from 0 to some time t1 of e at t minus l at t dt. Now inside the integrand, you can use whatever variable you want in order to not get confused because of the two t's over here. I know that my actual values, even though the question says time t, I'm going to be using time t1 to represent that. As long as you know where it is and then you confirm that, you clarify that within your answer, you won't lose marks for it. But you could use like the integral from 0 to t of e at s minus l at s with respect to s. You're taking the integral, that's fine because you're going to get the t in the end anyways. Okay, and so remember with the candidates test or the first derivative test, when we take the derivative, using the fundamental theorem of calculus, we're taking the derivative of an integral, so we sub in this top point, so I'm going to get e t1 minus l at t1 And now we have to find our critical points and then our endpoints. So to find our critical points, just set E at t, in this case, minus L at t equal to 0. And when you plug that into your calculator, you get time t equals 6.204. Now keep in mind, the reason why I'm able to do these calculations this fast on my calculator is because at the very start, I defined my functions. And so in this case, all I had to do was solve E at t minus L at t equals 0. That's all I had to do. And depending on your calculator, you might not even have to do the equals 0 because the solve will default to an equals 0. And so it's a matter of 2 seconds and you instantly get your answer. And so I get t equals 6.204. So now I'm going to create a table. That's usually what I do for these. I'm going to have a value t and I'm going to have my value f at t. So keep in mind, I'm going to test my endpoints, 0, my critical point, and then my other endpoint, so 0, 6.204, and 8. I'm going to plug these values into f at t. Now, right now I'm defining my f at t because I forgot to earlier, because originally I didn't need it, but now I do. So it's the integral from 0 to t of this function e at t minus L at t. And then in my calculator, I'm going to make a table. So I can input my t values and I can output my f at t values. And so at time t equals 0, well, this is kind of intuitive that the number of fish is 0 because you're taking the integral from 0 to 0. So the total area underneath this curve would be 0. At time t equals 6.204, my fish value is 135.01. And then at time t equals 8, I'm getting 80.91. Okay, so sorry, I'll just do a little separation. So what do we find? Well, at this specific time, this is the maximum value. So the maximum number of fish occurs at time t equals 6.204, and then when it says justify your answer, I would just say by the candidates test. Alright, and technically the work that you've shown should be enough, but just in case, it doesn't help to include the candidates test in your final answer as well. And so that's my final answer. So usually you will get things like this where you have to use multiple different concepts in one question. So in this case, we had to not only use the fundamental theorem of calculus earlier, but also explain the first derivative test to identify where the absolute maximum is, and then interpret that with respect to the answer. Alright, so moving on to part D. Is the rate of change in the number of fish in the lake increasing or decreasing at 5 a.m., so t equals 5? And explain your reasoning. Okay, so in this case, I see that I'm trying to find my rate of change behavior. Now keep in mind that the rate of change is the first derivative in context. So the change, or the behavior of the rate of change, would be the second derivative in context. Alright, so using that idea, I'm going to define another function in this case. I'm going to define r at t. This is going to be my total rate of change. So r at t is equal to, now this time because we're working to find the net rate of change, I can directly do e at t minus l at t, because both of them are rate of changes, so subtracting them we get the total, or the net rate of change. And then I'm going to take the derivative of this. And then in this case, no fundamental theorem needed. This is just term by term differentiation. So it's e prime at t minus l prime at t. And so what do we need to find? Well, at time t equals 5, we have r prime at 5 is equal to e prime at 5 minus l prime at 5. And then plugging that into my calculator, I get negative 10.7228. Alright, so what do I notice here? Well, this value is less than 0, and thus r at t is decreasing, and thus the rate of change is decreasing. And so that's our answer. If you wanted to provide a justification in your final answer, you could say as the first derivative is less than 0, or by the first derivative test, which can be interpreted outside of just extrema and to talk about behavior. Other than that, it's important to recognize that this rate of change function is not the same as the function in the last part, which was the total number of fish. So it's important to interpret both of them separately in terms of what the question is asking. And so that is question number 1 of part A. In terms of our timing so far, the video so far is 16 minutes long, so I'd say I spent about maybe 12 minutes on this question out of the 30, and that's really good time that you should be making, because with enough practice, you'll be able to on the actual AP exam have about 5 to 7 minutes to check over your work. And that is a crucial amount of time to have, because you'll catch any arithmetic errors you may have missed as you were working through it. So question number 2, this is a question that's solely focused on BC topics. This is also very common to get a question on either parametrics or on polars. In this case, we have it on polars. So what do I see? I see that I have a graph of the polar curve r of theta, which is equal to 3 root theta times sine of theta squared. And the range of these theta values are from 0 to root pi. We're asked to find the area of S. Now in a question with such a complicated theta curve, usually it helps because the AP testing usually gives us a pretty easy question to start things off. So the area of a polar curve, it's a formula that you guys should all know. The area is equal to 1/2 times the integral from our theta 1 to our theta 2 of my r at theta squared d theta. And so that formula is definitely something that you should be memorizing. And so what we find is that in terms of this specific curve, we get our area is equal to 1/2 times the integral from 0 to root pi of our r of theta function squared d theta. Of course, this is definitely not an integral that you want to be calculating, if you even can, by hand, and so just plug it into your calculator. So I defined my r theta in my calculator, I plugged in this expression, and I got 3.53429. Now, an important thing to consider about when you're writing the AP exam is significant digits. In this case, my calculator gave me 6 significant digits. 6 is a little bit too accurate. You're expressing a degree of confidence that you should not have about your answer. And by that, I mean it's a little bit too accurate to interpret with how, I guess, broad or how much error there could be with your calculation. So the general rule of thumb is to go anywhere from 2 to 4 significant digits. To be on the safe side, I always like putting 4. That's usually what the College Board testing recommends as well. And so I'm going to just round this off as 3.534. And in this specific case, there's no exact units that they've given us. So if you wanted to, you could say that the area of S is 3.534. you could say 3.534 units squared, because we're not given the units. That should work. So that's our final answer. An easy way to start us off, because now we get into the more challenging problems. So what is the average distance from the origin to a point on the polar curve given before for that range? So keep in mind once again that we want to find the average distance. Now what's important here is that it's from origin. Now, why is that important? Because one of the big mistakes that people made was on this specific question, they tried to do the average value of the arc length and not of the distance from the origin. Now, why is that different? Well, the arc length is the total length of the curve. And so the average would be the total length of the curve divided by the interval on which that curve exists. However, think about what actually it means to get the average distance from the origin. Well, what is the r in a polar curve? The r is that distance from the origin, isn't it? And so essentially, this question is made a lot easier if you interpret it correctly, because we're just trying to do the average distance or the average value of our r of theta function, not of the arc length function. And so we get our distance average is equal to 1 over, sorry, I will erase that. It's 1 over root pi minus 0 times the integral from 0 to root pi of r of theta d theta. The arc length formula is much more complex. The arc length formula involves r of theta and the derivative under the square root. It's definitely not that confusing, this question, as long as you interpret it correctly, that it's the distance from the origin, not the distance traveled. And so plugging this into our calculator, we get the value 1.5799. And then once again going to four significant digits, it's 1.580. And then once again, you can include units as your answer. And if you wanted to do a full sentence statement, you could say, well, the average distance from the origin to a point on the polar curve is 1.580. Alright, so that was just another formula. Do you know the average value formula? I'll restate it on the side over here just in case. I did earlier, but it's okay. It's 1 over b minus a times the integral from a to b of f at x dx. And keep in mind that a and b are the bounds of the interval, so in this case it was 0 and root pi. Alright. Question 2c. I see something that you don't normally encounter. There's a line in relation to a polar curve. It says that there's a line through the origin with some slope m that divides the region S into two regions with equal areas. Write but do not solve an equation involving one or more integrals to find m. Now keep in mind over here that this last statement, first of all, what you should notice is that it says do not solve. So do not try and spend your time trying to rearrange or anything. Just give that first equation that you would normally write out, and that's the answer. Second of all, I see one or more integrals. Now, this isn't always the case, but a lot of times when you have this additional wording, one or more integrals, a lot of the times you're going to have more than one integral. And so while that isn't necessarily like a surefire way to check whether your answer is correct or not, and you just have to believe that you did do all the steps correctly, it is a way, if you have one very simple integral and they're not asking you to solve it, it's very suspicious compared to if you had like two integrals or one complex integral, that it would make sense that you wouldn't solve it. And then it says the solution gives the value of m, not necessarily a direct rearrangement to solve for m, so you can just give that first line once again. So for this specific question, I would recommend drawing out what it might look like. Just a very rough sketch. It's a terrible line, sorry. I'll try and do it a little bit straighter. Something like that, where it was going through the origin and both parts would have equal area. Alright, so what do we have to consider now? Well, if you look at this point, right here, I'm going to say that's point H. Alright? What are the coordinates of point H? Well, we could express it as some value theta. So when we have this intersection, we have some value theta over here that this polar curve has traveled, and we have some distance r. Except what do we know as well? Well, we know that the coordinates of H, because this is a polar curve on the Cartesian coordinate plane, we can rewrite this as x, y, right? And so this is where you have to consider not only just polar equations, but or like area of polar curves, but also you have to consider about the geometry. And so in this case, what do we have? Well, we have a triangle that we can draw. This is theta, this is the origin O, and then this is our point H. Now, if H has the coordinates x, y, then this triangle has a length of y, this has a length of x. And sorry, I should make this clear that this is going to be a right angled triangle. So what do we notice then? Well, we notice that, keep in mind we're given that the slope is m. So our slope is equal to m in this case, right? Now what is slope? Well, it's equal to our delta y over delta x. In this case, that's just going to be y over x. For that point h, x, y, where this line meets the polar curve, again, after it intersects with the origin. But what else do we know about this triangle? Well, I see that tan theta is also equal to y over x. And this has to be equal to m. So I'll do a single underline so it doesn't look like it's the answer. And so what I get is that my theta is going to be the inverse tangent of m. So that theta value we've now solved for as being the inverse tangent of m. Okay, so now what do we know? Well, we already know that the two regions are going to have equal areas. And so what can we do? Well, the area of this first region, so on the graph, I'll color that in green, I guess. Sorry, you can't see that. I'll use the darker green. So that first region, if we consider the area, was the integral from 0 to our new theta value, the inverse tangent of m, of our function r at theta squared with respect, the integral taken with respect to theta. Alright, that's just the area of that first section by the definition of, oh sorry, there's a 1/2 as well in front. So that's the area of that particular polar curve going from 0 to the inverse tangent of m, which is that new theta value that we found. Now what do we also know? Well, this is just half of the total area, right? And we already found earlier that the total area is equal to 1/2 times the integral from 0 to root pi of r at theta squared, the integral taken with respect to theta. And so, because this is the total area, we have to multiply this total area by 1/2 again to get half of that total area. And so if you wanted to do one simplification step, that the only one that I would suggest that you do if you wanted to is cancel out these 1/2. So I can get or the integral from 0 to the inverse tangent of m of r at theta squared d theta is equal to 1/2 times the integral from 0 to root pi r theta squared d theta. So either one of these will work. It's just you have to know that this, either the top or the bottom, that's the expression that you should be getting. This is a very heavy interpretation question. It not only asks you to relate angles to slope, which is probably a relationship that you should know, is that the tangent of an angle is equal to the slope of the adjacent hypotenuse line, and that's true for any right triangle. Not only that, but you should also know that, of course, the area of that first segment is equal to half of the area of the total, because they're equal areas, and then it's just a matter of mashing up the two parts of the information you know into one equation. So that was a very challenging question. Now for part D, we have for k greater than 0, A at k is the area of the region S that's also inside the circle. R is equal to k cos theta. Find the limit as k approaches infinity of A at k. Now for this specific one, what I'd suggest doing, and what I'm doing right now, is I'm going to first show what R is equal to cos theta looks like. It looks something like that. That circle right there is the function R is equal to cos theta. Now in a slightly different color, what happens if I go R is equal to 3 cos theta, for example? Well, I start to get this, something bigger, but still only to the right hand side of the y-axis. If I do one more iteration, I get something maybe like that. Sorry, that was a really bad drawing, but you get the idea. It's going to constantly stay to the right. However, as the limit of k goes, as k goes to infinity of R is equal to k cos theta, so that function, it's going to become all of quadrants 1 and 4. Right? It's going to encompass all of the right hand side of the y-axis. And so what do we really need to do? Well, our value A at k is going to be the area of S in quadrant 1. Why? Well, because again, inside the circle, it's only going to be the area or the region S that lies within either the first or the fourth quadrant. But as you can see in the diagram, none of S is within the fourth quadrant, so it has to be within the first. And so now we again use this area formula. So we get 1/2 times the integral from 0. Now this time we're not going to go to root pi. This time we're going to go to pi over 2. Because as we go from our positive x-axis, so theta is equal to 0, to our positive y-axis, we're traveling a total of 90 degrees. So our theta becomes pi over 2. And then again of r theta squared d theta. And so for this particular one, because it doesn't say do not solve, so you probably should solve it. And so you get the value of 3.324. And this lies in the range of 4 significant digits, so this is the answer that I would provide on the AP examination. So why was this an interesting question? Well, this isn't like your normal limits, because there isn't a direct substitution. If you did a direct substitution into infinity times cos theta, you get an oscillating function. And finding that limit wouldn't necessarily help you in terms of this question. So what's important is that you consider the geometry of it, and that's a lot of times the most important thing when you're working with polar curves, is identifying the geometry involved so that you can interpret the question properly and use then the appropriate formulas. So that was question number 2. Now we're moving into the section, part B, where there is no calculator. Now in this case, because of my explanation, I'm currently a little bit above, so I'm at 35 minutes right now, but with the 5-minute introduction and whatnot, I'm probably at around 30 minutes, which means that I used exactly the maximum amount of time to not only explain my concepts, but also to do my work. And so that's something you should aim for, because now on the actual AP exam, you'll be able to easily reach the 30-minute mark. Alright, so for question number 3, I see no calculators, and I see shapes that I can use geometry to calculate the integral. Probably done unpurposely. So for part A, I say if the integral from -6 to 5 is 7, and the integral from -6 to -2 is a value that we're trying to find, how do we find that value? Alright, so first of all, what I notice is that I can split this integral. So this original integral is equal to the integral from -6 to -2 plus the integral from -2 to 5. This is just a property of definite integrals that you should know. We're given that the left-hand side is 7. I'm going to replace our unknown value with alpha, and then I'm going to solve for this remaining. Now, looking at a little bit of geometry, I'm going to show that, as you can see on the graph, these two triangles will cancel out in terms of their area, because one's positive, one's negative, but the magnitude is the same. So they'll cancel. Same thing over here. These will cancel. So now we're just left with these two other shapes. For the one in purple, it's a trapezoid. I have height of 1. I have a base of 1, another base of 3, and then remember we divided by 2. So again, area of 2. Alright, so I get plus 2 plus. Now in this case, where the blue is this area, if you notice carefully, you see, even in the question, it said there's a quarter circle, the area underneath that quarter circle. Well, if you interpret it geometrically, I see a quarter circle, but I also see a square, a 3x3 square that holds that quarter circle. And so that area can be interpreted as the area of the square minus the area of that quarter circle. And so the area of the square is just 9 minus the area of the quarter circle, which has a radius of 3, and so I get 9 minus 9 pi over 4. And so solving for alpha, I get 9 pi over 4 minus 4. And so that should be the final answer. In this case, again, you could include the units. If you're running short on time, it's not necessary. If you have the time, then it doesn't hurt to. Okay. Evaluate the integral from 3 to 5 of 2 times f prime at x plus 4 dx. Alright, so what am I going to do? Well, I'm going to say that this integral can be split up into its components. I'm going to do a couple of steps. So for this first integral, I'm going to pull out the constant. For the second integral, it's just 4. Alright, and so what we get is that, what can I do here? Well, I see a derivative inside an integral. So that just, by the fundamental theorem of calculus, becomes the original function. And then the integral of 4 is 4x. We're going to evaluate these at their bounds, and keep in mind you don't need the plus c because it'll just cancel out when you're evaluating your bounds. So, what do we get over here? Well, I see that f at 5 is equal to 0. F at 3 was a value we were given. It was 3 minus root 5. If you go back to the question, you'll see that. And then plus 4 times 5 minus 3. And so this becomes 2 root 5 minus 6 plus 8, which becomes 2 root 5 plus 2. And that's our final answer. So that wasn't necessarily that hard of an answer. It's just working through, and then knowing your fundamental theorem of calculus is probably the most important concept here. And then looking back at the question to make sure that you actually found out what f at 3 was. It was given in the question, but it was a little bit subtle, and if you tried to work it out algebraically, you would get it, but it would take a while, and that's time that you could have used somewhere else. So keep in mind to read the question. Alright, so for part C, the function g is defined by g at x equals the integral from -2 to x of f at t dt. Find the absolute maximum value of g on this interval -2 to 5. Justify your answer. Alright, so what I'm going to do is I know that I'm trying to find an absolute max. So once again, I'm using the candidates test. And so I get my g prime at x is equal to f at x. Sorry, no differential over here, so no dx. Remember, we have to test our endpoints and our crit points. Alright, so f at x is equal to 0 when x is equal to, I see -1. This middle one, you could calculate the slope and the equation of the line, or you can just use the slope and say that, okay, if my slope is 2 along that line between x equals 0 and x equals 2, that slope is 2, that means that it intersects the axis at the point 1/2. And then we have our final point at 5. So once again, I'm going to set up my little table. So x, g at x, I'm testing -2, -1, 1/2, and 5. In this case, 5 is both a crit point and an endpoint, which is why we only have 4 things instead of 5. Alright, so at -2, our integral is going to be 0 because you're evaluating it, the upper and the lower bound are the exact same. At -1, well, looking at it geometrically, I see a triangle with height 1 and base 1, so there is going to be 1/2. From -2 to 1/2, well, these first two triangles are going to cancel out like we showed at the very start, and then we're going to left with a smaller triangle below the x-axis. This triangle has a height of 1 and a base of 1/2, and so the area is going to be 1/4. Keep in mind, because it's below the x-axis, it's negative. And then at 5, you can calculate it again, and you'll find that you have these two things that cancel, these two sets of triangles that cancel. We have a trapezoid with area 2, then we have an area under the curve we have a thing underneath the quarter circle with an area of 9 minus 9 pi over 4. So our total thing becomes 11 minus 9 pi over 4. Alright, it's fairly obvious which one is the maximum. If you weren't sure, because this is a no calculator, the easiest way to check is that pi is 3.1415, etc. So it's less than 4, which means that pi over 4 as a fraction would have to be less than 1. 9 times a value less than 1 has to decrease. So from 9 it would become 8 point something or 7 point something, depending on how low that value was. And because of that, 11 minus your resultant value would have to be at least higher than 2. And so because of that, this value greater than or equal to 2 is going to be the maximum. So that occurs at x equals 5. And then justification by the candidates test. Alright, so that was a fairly simple question. This one was one that may have thrown people off a little bit, because it's a limit that you don't normally see, because in fact, when you look at it carefully, you can just substitute. There's no additional tricks involved with it. Now, how do we verify that we just substitute and we don't have to use something like L'Hopital's rule? Well, this denominator that we see, f at x minus arctan x, if you plug in 1, f at 1 is 1, but arctan of 1 is pi over 4. 1 minus pi over 4 is not 0 in the denominator. And so regardless what's on the top in the numerator, there is no using L'Hopital's rule in this. And so your best bet is to just try substitution before you try and do any more manipulation. Usually there will be some free questions like this. So I'm going to say that this limit, which is equal to L, so L is equal to 10 to the power of 1, which is 10, minus 3 times f prime at 1 over f at 1 minus pi over 4. Now what is f prime at 1? Well, once again, similar to how we found that root on that line, if you calculate the slope, so the rise over run, you get a value of 2. And because it's a line, the tangent to the line is just that line itself. So the slope is just going to be the slope of the original line. So f prime at 1 is going to be 2. 10 minus 3 times 2 is going to be 4 in the top. F at 1 is 1. So 1 minus pi over 4. And you don't need to simplify any further. Even though it might only be one step, don't bother. This is, if you do try and simplify it, that's also where the greatest chance of error is going to be. Just leave it like this. Very easy question to get through. Alright, so moving on to question 4. Our timing is pretty good. We're at 46 minutes right now. We have, remember, a total of an hour and a half across the entire 2 sections. So we're making good time. So question 4 says a cylindrical barrel with diameter of 2 feet collects rainwater. We have a rate of change of height given to us, and we're told that the volume is pi r squared h, which is a formula that you may already know, but they give it just in case. And the question says find the rate of change of the volume of water in the barrel with respect to time when the height is 4 feet. Now in this case, I see that I have 2 variables that I would have to differentiate with respect to time, r and h. So if I were to implicitly differentiate as of right now, then I would need to use product rule, and I would get a decently long expression that I would need to substitute everything into in order to ensure I get my final answer. But are there any tricks? Not always, but in this case, yes. Because we're told that the diameter is 2. And the diameter isn't going to be changing. And so the radius is also not going to be changing. It's going to be stuck at 1. So for this particular case, my volume is equal to pi r squared h, but it's actually just equal to pi h. So now if we differentiate with respect to time, my dv by dt is going to be pi times dh by dt. And using the expression that we're given, it's pi times negative 1/10 root h. And remember, we're evaluating this at h is equal to 4, as the question says. So what is this going to give us? Well, root of 4 is 2, negative 1/10 times 2 is negative 1/5. So I get my final answer as being negative pi over 5. And then it says to indicate units of measure. Now our volume, remember we're doing the rate of change of volume, so our height is measured in feet, thus our volume must be measured in feet cubed, and then it's feet cubed over time, so over seconds. So it's feet cubed per second. And so that would be our final answer. So just a simple related rate involving implicit differentiation. And even though it's not that much step, if you didn't recognize that r is equal to 1 is a constant, you could differentiate fully using product rule, saying that it would be 2rh dr by dt plus r squared dh by dt. You just have to recognize that then my radius is 1 and my change in my radius, so dr by dt, is 0, and you get the same answer. Alright, so moving on to part B. When the height of the water is 3 feet, is the rate of change of the height of the water increasing or decreasing? So this once again goes back to the idea that we saw in question number 1, where it's ROC behavior in context is the second derivative. And so what do we have? Well, we have dh by dt, negative 1/10 root h, right? So you want to find the derivative of this, so the second derivative, so it's d squared h by dt squared. What's this equal to? Well, I'll put my constant out. Differentiating root h, I get 1 over 2 root h. And then remember, by chain rule, I have to multiply by dh by dt. And so actually this is 1/10 times 1 over 2 root h times, well, we resubstitute our value of dh by dt. So we get negative 1/10 root h. And so our final answer turns out to be 1 over 200. It's independent of the height. And so even though they give you the height of the water in this question, it doesn't even matter, because we have a value 1 over 200, which is greater than 0. And so we know that the ROC, the rate of change of height, is increasing. Alright, and so once again, if you were to explain the reasoning, you could say by the first derivative test. And then I would put it in brackets, first derivative greater than 0. Alright, so that's part B. So as you can see, after those challenging questions at the start, stuff starts to move very quickly. This is a question where I see the word separation of variables. Instantly, what do I think? Well, the only thing that really involves separation of variables is a differential equation. So good to review differential equations because they do come up on the AP Calculus exam. Alright, so at time t equals 0 seconds, the height of the water is 5 feet. Use separation of variables to find an expression for height in terms of time. Okay, so what do I know? Well, I know that dh by dt, again, is negative 1/10 root h. So that means that 1 over root h dh is equal to negative 1/10 dt. Keep in mind, separation of variables means that the main variable you're solving for, all terms regarding that are on one side, preferably the left side, and then the constants and the leftover terms are moved over to the right side with that second variable. So in this case, it would be t, and our main variable is h. And so in this case, I separated my variables, and then I can take the integral on both sides. And so what I get is that the integral of 1 over root h becomes 2 root h, and then that's equal to, well, the integral of negative 1/10 is negative 1/10 t. And then remember to include plus c. A lot of the times in differential equations, just including this plus c will get you a point, because it's a thing that people mess up. So if you solve this, remember that you only need the plus c on one side, because if you put it on both sides, you can just rearrange and put the two c's together, and a constant subtract a constant, it's just going to be another constant. So you just have that plus c. Now what else do we know? Well, if we evaluate this at time t equals 0, where h is equal to 5, then I get 2 root 5 is equal to negative 1/10 times 0 plus c. So my c is equal to 2 root 5. And so using this information, I'm going to get the expression that 2 root h is equal to negative 1/10 t plus 2 root 5. So root h is equal to negative 1 over 20 t plus root 5. And then h is equal to negative 1 over 20 t plus root 5 all squared. And so that's your answer, as for h as a function of t. So that was just simple differential equations. I will let you know that question 3 and question 4 were both part of the AB exam as well. This particular one, question 5, and I believe question 6 as well, are unique to BC. So these are ones, over here I already see a quadratic in the denominator. Most of the time, well, a quadratic in the denominator represents what? Well, it represents partial fractions, right? And that's a BC only topic. So most probably there's going to be something regarding partial fractions. So it says consider the family of functions f at x is equal to 1 over x squared minus 2x plus k, where k is a constant. And part A says find the value of k where k is greater than 0, such that the slope of the line tangent to the graph at x equals 0 is 6. Alright, so let's take the derivative. So my f prime at x is equal to, well, keep in mind that if we have 1 over x, for example, then the derivative becomes negative 1 over x squared times the derivative, which is just 1. The same principle can be applied over here. So the derivative is going to be negative 1 over x squared minus 2x plus k all squared, and then times the derivative of this denominator, which is going to be 2x minus 2. Alright, and so I'm just going to rewrite that as negative 2x minus 2 over x squared minus 2x plus k squared. If you don't know how to solve it in your head, then you can just write it out as the denominator to the power of negative 1 and then take your derivative using power rule and then chain rule. So that should be your final answer. Now we're evaluating this at x equals 0, such that my f prime at x is equal to 6. And so plugging that in, I get 6 is equal to, well, if I plug in 0, then I get 2 times 0, which is 0, minus 2, which is negative 2, and then times this negative 1, so I get a 2 on the top divided by 0 squared is 0, 2 times 0 is 0, so I'm just left with a k squared on the denominator. So then I see k squared is equal to 1/3, and k is equal to plus or minus root 1/3. However, we're only considering the values of k greater than 0, and so we have our only value. And also look at the question, it says find the value of k. That indicates that there's a single one, and so if you did get multiple answers for some reason, if you took your derivative wrong and you got multiple answers, this is a great way to check. Why do I have 2? The question only asks for 1. So my k is equal to plus square root of 1 over 3, which is equal to just 1 over root 3, or if you'd like to rationalize, root 3 over 3. Both of those answers will work. And so that was question number 1. Question number 2 says, for k is equal to negative 8, find the value of the integral from 0 to 1 of f at x dx. Alright, so what do I have? Well, I have the integral from 0 to 1 of 1 over x squared minus 2x minus 8 dx. Alright, well guess what? This denominator will factor. So I'll have, when I'm doing my partial fraction decomposition, which is the term for this procedure I'm going to do, where you're splitting up a fraction into the sum of individual linear denominator factors. So I get some value a over my first factor, which is going to be x minus 4, plus some value b over x minus 2. Now you could work through the algebra on this by cross multiplying and then setting the numerators equal. In this case though, it might be a little easier honestly if you restate it like this. As you'll see, I'll write 1 over x minus 4 and then just rewriting this right hand side. And then what I like to do is I like to use the shortcut, the cover-up method. Now what is the cover-up method? Alright, so let's say for solving for a, our denominator is x minus 4. What sets that denominator equal to 0? X equals 4, right? In my original fraction, which is this 1 over x minus 4 times x minus 2, I'm going to hide the x minus 4 factor, and I'm going to plug in 4 for the other x's. So in this case, if I hide my x minus 4 factor, I'm left with 1 over x minus 2. Plug in 4, I get 1/2, right? So my a value is going to be equal to 1/2. Alright, similar thing over here. My b value is going to be, I have an x minus 2 on the denominator. Oh, sorry, this is plus 2. Not minus 2. The factors are x minus 4 and x plus 2. Alright, so using this cover-up method again, sorry. So x is equal to 4, cover up the x minus 4 factor, I get 1 over x plus 2. When x is 4, my a is 1 over 6. My b value, well, what makes the denominator equal to 0? When x is negative 2. Cover up the x plus 2 factor in the original, I get 1 over x minus 4. When x is negative 2, I get 1 over negative 6, or negative 1 over 6. This cover-up method is a really good shortcut, and it will work for any partial fraction decomposition as long as the factors are linear on the bottom. Once you get irreducible quadratic factors or powers, so if I had like x minus 1 cubed, then the cover-up method isn't as useful. But at the same time, you can generally just integrate those types of functions normally without using partial fraction decomposition. So it's not that much of a trouble. So I'd say 95% of the time, this cover-up method is the faster and better way to go. So I now have the integral from 0 to 1 of 1/6 over x minus 4 plus negative 1/6 over x plus 2 dx, which is equal to 1/6 times the ln of the absolute value of x minus 4, and then minus 1/6 times ln of the absolute value of x plus 2, and then all evaluated from 0 to 1. Alright, so what do we get? When I plug in 1, right, I get 1/6 ln of, now 1 minus 4 is negative 3, but remember it's the absolute value, so I just get ln of 3 minus 1/6 of ln of 3, because 1 plus 2 is now 3. So this is my first part when I plug in 1. And minus what happens when I plug in 0. Well, I get 1/6 ln of 4, because 0 minus 4 is negative 4. Absolute value of that becomes positive 4. Then minus 1/6 ln of 2. And so what does my final answer become? Well, these first two terms will cancel out. I have negative this expression, so my final answer becomes 1/6 ln 2 minus 1/6 ln 4. Or if you want to do a little bit of factoring and simplifying, I get 1/6 ln of 1/2. And if you want to use some log rules, I get negative 1/6 ln 2. Either one of these three expressions should suffice. I'd go with one of the last two just to be safe. I believe the official answer for this was this very last one. But all of these are equivalent expressions, and they are fairly simplified. Alright, so I'm just going to underline this last one as an accepted answer, but all of those should work. So this is just using partial fraction decomposition. This next one, however, is an interesting question. Because it says for k is equal to 1, find the value of the integral from 0 to 2 of f at x dx, or show that it diverges. Now, a lot of times this is an indication that there is going to be some divergence. So let's work through our value k is equal to 1. So I get from 0 to 2 of 1 over x squared minus 2x plus 1 dx, which is equal to the integral from 0 to 2 of 1 over x minus 1 squared dx. What do we notice here? This is an improper integral. Why? Because there's very clearly a discontinuity at x equals 1, right? So our x cannot be equal to 1, except 1 lies within the bounds of the integral. And so we're going to have to split this integral as the limit as some value a approaches 1 plus, sorry, in this case it would be 1 minus. So limit as a approaches 1 from the negative side times the integral from 0 to a of 1 over x minus 1 squared, and then plus the limit as some value b approaches 1 from the positive side of the integral of b to 2 of 1 over x minus 1 squared. Now what did I do here? I essentially broke up my integral as going from 0 to 1 and 1 to 2, but because there's a discontinuity at 1, I'm saying that we're taking the integral, the area under the curve, as close to that value 1 as we can without actually touching 1. So we're taking the limit as it goes to 1 from the negative side, as close as possible, infinitesimally close, and then from the other side, I'm going from 1 from the positive side, so just a little bit after 1, a minuscule amount after 1, all the way up to 2. And now what do we get? Well, we get this same limit as a approaches 1 minus of, well, what's this integral going to evaluate to? Well, if you have 1 over x minus squared, you can do a simple u substitution if you want, or you can just calculate it and you'll get negative 1 over x minus 1. So I get negative 1 over x minus 1. This is going to be evaluated from 0 to a, and then plus the limit as b approaches 1 plus of this same negative 1 over x minus 1 evaluated from b to 2. Now, specifically for this case, both of these will diverge. Both of these portions of the integral will diverge. The reason being that, now keep in mind, for showing divergence, only one of the sections has to diverge, because if you have infinity as one thing, it doesn't even matter. The integral still doesn't exist. And so, especially because it's addition here. And so what I'm going to show is that this limit becomes, and on the actual AP exam, you can just say that this limit diverges as a approaches 1 minus. I'm going to show you exactly why though. Because think about it, if you plug in a over here, right, I get negative 1 over. Now let's think about what happens if you're going really close to 1 from the negative side, and then you subtract 1. You're going to get really close to 0 from the negative side, right? Like let's say if you have 0.9, and then 0.95, and then 0.99. You're getting closer and closer to 0 from the negative side. And then minus negative 1 over, when I plug in 0, I get negative 1. But what happens when I get negative 1 divided by 0 from the negative side? I just get positive infinity. Minus 1. So I get infinity. So if an integral has the value infinity, it does not exist, or it diverges. And then I can say, because the first integral diverges, the integral from 0 to 2, of f at x dx also diverges. Now this first integral, you could restate it as the integral from 0 to 1 of 1 over x minus 1 squared, or you can use the limit as well and restate that. And then for the second one, I'm not going to write it out because it's the very similar idea of, okay, well, if I plug in 2, I'm going to get a concrete answer. When I plug in my b value, right, I'm going to get, I'm going to take the limit as b goes from 1 to 1 from the positive side. So I'm going to approach 0 from the positive side. So actually, I'll just show it. So this becomes, when I plug in 2, I get negative 1, and then minus negative 1 over 0 plus. And in this case, it actually is, sorry, I should backtrack. It actually is important to show that the second integral diverges in a certain way, because there is the possibility that you get infinity minus infinity. So sorry, I should have said that earlier. There is the chance that you get infinity minus infinity that is not indeterminate. That will actually evaluate to, sorry, let me try and refresh my memory on indeterminate forms. I believe infinity minus infinity does evaluate to 0, but sorry, no, infinity minus infinity is an indeterminate form. Right, it's infinity plus infinity that evaluates to positive infinity. But infinity minus infinity is indeterminate. And so I guess I was right the first time. You don't need to show that the second one diverges because if one of the components diverges, it'll either be indeterminate or it'll be infinity. And so it doesn't exist regardless. But to show you guys, this would become -1 plus infinity in this case because I'm taking -1 over 0 positive. So I get negative infinity and then subtracting, so I get positive infinity, and then infinity plus infinity is just infinity. So the overall integral doesn't exist. And you could show all of that work, or you could show just this first part, and both of them should be considered accurate because it's sufficient evidence. All right, so just giving a quick update on time. Right now we're at 1 hour and 10 minutes, sorry. So we're making good time, good progress. All right, so this is the last question, and normally this last question, as you can see here, does involve something about Taylor series or Taylor polynomials. So if function f has derivatives of all orders for all real numbers x, we're given a graph, and then we're given a table with all the important derivatives, and we're asked to find the third degree Taylor polynomial for f about x is equal to 0. All right, so in this case, what do I like to do? Well, I like to just use, in this particular case, a formula. F at h plus x. This is the formula for a Taylor polynomial. This specific one, I'm going to do the third degree Taylor polynomial. This is equal to f at h plus f prime at h times x plus f double prime at h over 2 factorial x squared plus f triple prime at h over 3 factorial x cubed. This is the third degree Taylor polynomial. Now what is our h in this case? Well, it's about x is equal to 0, so our h is 0. So we get f at x is equal to, well, what's f at 0? We're given that it's 3. What is f prime at 0? Well, good thing we're given the tangent graph at x equals 0. The slope of this graph, as you can see, I'm going to use the point 0.03 and the point 1.1. So my rise over run is -2 over 1, so it's -2. Plus, now we just use the table, so our second derivative is going to be 3, so it's 3 over 2x squared. And then plus -23 over 2 over 6x cubed. And then simplifying this a little bit, we should get 3 minus 2x plus 3 half x squared. So 3 minus 2x plus 3 half x squared minus 23 over 12x cubed. And then as you can see, this is the third degree Taylor polynomial because you have the maximum degree as being 3. This formula is one that you probably should know to make these questions significantly easier rather than trying to derive it from a Taylor series, because while that is possible, this one looks so much cleaner than writing out the general formula for a Taylor series and then finding out the first few terms of it. Alright, write the first 3 non-zero terms of the Maclaurin series for e to the x. Then write the second degree Taylor polynomial for e to the x times f at x about x is equal to 0. Alright, so the Maclaurin series of e to the x is equal to, this is one that you should have memorized, going from n is equal to 0 to infinity of x to the nth over n factorial, I believe. And so what we get is, because it's all positive in this case, this is not an alternating series, and so we get our first three terms as being, well, when n is equal to 0, I have 1 plus x squared over 2, or x squared over 2 factorial, whichever one you want to use. So that was this first three non-zero terms. Now, if we're trying to write e at x times f at x, keep in mind, now we're trying to do the second degree Taylor polynomial. So think about this. Now, we have to multiply each of the terms by each other in this case. When you're multiplying two Taylor polynomials, or in this case, this 1 plus x squared over 2 is a Taylor polynomial as well, about x equals 0, we have to multiply all the terms together. And so I get this first term 1 is going to have to be multiplied by all of the terms up to degree 2. So I'm going to have, if we look back, our thing was 3 minus 2x plus 3 half x cubed. So 3 minus 2x plus 3 half x squared. And then I'm going to have plus x times, now in this case I only want to go up to this minus 2x term, because when I multiply x and minus 2x, I'm going to get my x squared term. Any higher than that, I'm going to get an extra term that I don't need. So I'm going to get 3 minus 2x. And then this last term, x squared over 2, I'm just going to need to multiply it by 3, because any term of higher degree, and I'm going to get a third degree value, which I don't need. And so now it's just a matter of doing the simplification. So I get 3 minus 2x plus 3 half x squared plus 3x minus 2x squared plus 3 over 2x squared. And so what is this equal to? Well, I have 3, I have plus x, and then I have minus x squared. And so my final Taylor polynomial is going to be 3 plus x, plus x squared. Because I have 3 half plus 3 half, which is 3, and then minus 2, which is x squared. So that is our final answer. Part C is, I believe, the second last one. It says, let h be the function defined by h at x equals the integral from 0 to x of f at t dt. Use the Taylor polynomial to find an approximation for h at 1. All right. So let's think about this. What was our f at x? Well, it was 3 minus 2x plus 3 over 2x squared minus 23 over 12x cubed, I believe. Let me just go back and check. Yep, minus 23 over 12x cubed. And so think about f at t just means that we're replacing these by t. And so I get h at 1 is equal to the integral from 0 to 1 of this value 3 minus 2t plus 3 half t squared minus 23 over 12 t cubed respect to dt. This is a very simple integral to calculate. I get 3t minus t squared plus t cubed over 2, and then minus 23t to the 4th over 48 evaluated from 0 to 1. Let me just check if I did that right. Yeah, I believe so. And then our final answer, when you work through this, if we plug in 0 into each of these terms, we're going to get 0, so we just have to plug in 1 and evaluate. So I get 3 minus 1, which is 2, plus 1 half, which is going to be 5 halves, and then minus 23 over 48. So I get 5 halves minus 23 over 48, which is equal to 97. So 97 over 48. And so that's our approximation of h at 1. Now, it's known that the Maclaurin series converges for that function h that we had. It converges to h at x. It's known that the individual terms for h at 1 alternate in sign and decrease to 0. Use the alternating series bound to show that the approximation found in part C differs from h at 1 by at most 0.45. This is one of those special ones where we have to keep in mind, we have to remember our error bounds, and luckily we're given a value, so we will know instantly if we're right or wrong if we did our error bound wrong, because it's not going to match with their value. So in a way, this is actually a very easy question. So remember, what is our error bound? Well, our error bound says that our remainder has to be less than or equal to the absolute value of our term evaluated at n plus 1 for the nth term remainder. Alright, so keep in mind our f at x was equal to 3 minus 2x plus 3 over 2x squared minus 23 over 12 x cubed. But then think about our f at x has constantly been evaluated at our third degree, right? But what's our fourth degree term? Because that's what we're going to need for our error bound. Our fourth degree term is 54 over 4 factorial times x to the fourth, which is equal to 4 factorial is 24. So 54 over 24 gives us 27 over 12x to the fourth. Alright, so our remainder at 3, because we're using our third degree, has to be less than or equal to the integral from 0 to, again, 1, because our x is 1, of 27 over 12 t to the fourth. Right? This is just because that is going to be our next term. And so our thing will turn out to be, sorry, did I do that right? 54 over 24 becomes 27 over 12. Oh, that can be further simplified actually. That's why, because it's the integral from 0 to 1 of, if you factor it to 3 now, it becomes 9 over 4 t to the fifth, which is equal to, now we can just say this is, sorry, it's t to the fourth. And then the integral becomes 9 over 20 t to the fifth, evaluated from 0 to 1. When you have 1, our answer becomes 9 over 20, and then 0 is 0, so our final remainder has to be 9 over 20, and so our absolute value of our remainder has to be less than or equal to 0.45 by the alternating series error bound. If you guys do need a refresher on these error bounds or on these things about series, like the Maclaurin series of e to the x, please be sure to check out my other video on that. It's titled Series Part 1 for the error bounds, and then even though we didn't have to use the Lagrange error bound for Taylor polynomials, that is a thing that has come up in the past. So if you want to review that, go check out my series Part 2. Alright, so that is it actually for the AP Calculus BC 2019 free response questions. We are currently at 1 hour and 23 minutes, which means that with the introduction, with a little bit of time spent, we still did have 10 minutes at the end to review our work, which is good timing, especially for how hard some of these questions were. Thank you so much, everybody, for watching this video. Big thank you to everyone for all your support to the channel. You guys have been really great and really supportive of my work. Remember to like the video if you gained anything from it, if you benefited, and if you enjoyed it. Comment down below for any other suggestions for future content. Remember to subscribe and hit that notification bell so you see when I launch my next video. Once again, thank you guys so much, and we'll see you guys at Patel Academy once again for the next video.